Hey everyone! In the last video, we looked at the physics of a single machine, the nanoseconds, the CPU cycles, and the distance of data. But today, I want to talk about what happens when you move from one machine to millions of users. And usually when we talk about scale, people immediately start talking about load balancers or sharding. But before we get to the tools, we have to talk about the math of scale. I want to start with a story from a launch I was involved in. We had built a new service and we were monitoring it closely. Our dashboard showed a beautiful flat line for average latency. It was 100 milliseconds. We were high-fiving each other. The system looked perfect. But then we started seeing the support tickets. Users were complaining that the site felt broken or glitchy. We looked at our average graph again, still 100 milliseconds. Flat as a pancake. It took us 3 hours to realize that we were looking at the wrong part of the math. While the average user was having a great time, 1 out of every 100 users was experiencing a latency of 15 seconds. Because we were looking at the mean, we were effectively blind to the suffering of 1% of our audience. And at our scale, 1% was 10,000 people. This is the myth of the average. If you want to be a staff engineer, you have to stop thinking in terms of average latency and start thinking in distributions. You have to become obsessed with the tail. Today, we're going to look at why averages lie, how to read a histogram, and why tail latency is the secret killer of distributed systems. Okay, so let's look at a graph. Not a line graph, but a histogram. Imagine you're measuring the time it takes for your server to respond to a request. If you just take the average, the mean, you're adding up all the times and dividing by the number of requests. The problem with the mean is that it's extremely sensitive to outliers, or even worse, it hides them. Think about a room with 99 people who make $50,000 a year and one person, let's say Bill Gates, who makes $1 billion. The average person in that room is a multimillionaire, but that's not true, is it? It's a mathematical hallucination. In system design, we use percentiles to solve this. You'll hear engineers talk about P50, P95, and P99.9. The P50 is the median. If you line up all your requests from fastest to slowest, the P50 is the one right in the middle. It's what the typical user experiences. But as a senior engineer, your eyes should always skip past the P50 and look straight at the P99 and P99.9. The P99 is the 99th percentile. It represents the slowest 1% of your requests. If your P99 is 2 seconds, it means 1 out of every 100 users is waiting at least 2 seconds. Now you might think, okay, Andre, 1% isn't that bad. We can live with that. But here is the first principle of scale. At scale, the rare event becomes the constant event. If you have a billion requests a day, a P99.9 failure, the 1 in 1,000 event, is happening 1 million times a day. It's not an outlier anymore. It's a permanent feature of your system. When you design for P99, you aren't just fixing bugs, you are engineering for the reality of high concurrency environments. You are moving from hope-based engineering to statistical engineering.
Now, why is the P99 so dangerous? It's because of a phenomenon called tail latency amplification. This is why your perfectly designed microservices can suddenly feel like they're running through molasses. Let's do some quick math. And I love this because it's so counterintuitive. Imagine you have a single service. It has a P99 of 100 milliseconds. That means only 1% of requests are slower than 100 milliseconds. Pretty good, right? Now, imagine you build a modern architecture. To render your homepage, your front end has to call 100 different microservices in parallel. This is actually common at places like Amazon or Google. Even if every single one of those 100 services has a 99% success rate of being fast, what is the probability that the total homepage request will be fast? It's not 99%. The math is 0.99 raised to the power of 100. Does anyone know what that is? It's roughly 0.36. Think about that. If your page depends on 100 services and each service is slow only 1% of the time, 64% of your users will experience a slow homepage. The tail of the distribution has amplified. The 1 in 100 problem has become the majority problem. This is the microservice trap. As you increase the number of components in your system, the P99 of the components becomes the P50 of the whole system. The exception becomes the rule. This is why at FANG-level companies, we don't just optimize for speed, we optimize for variance. We would rather have a service that is always 50 milliseconds than a service that is usually 10 milliseconds, but occasionally 500 milliseconds. Predictability is more valuable than raw speed when you are scaling horizontally, because in a distributed system, you are only as fast as your slowest component.
So, we understand the tail. We understand that the P99 is the real enemy. But now we have to talk about how to actually move work through the system without the tail exploding. This brings us to the two fundamental pillars of performance: throughput and latency. A lot of people use these terms interchangeably, but they are very different animals. Imagine a highway. Latency is the time it takes for a single car to get from point A to point B. If the highway is empty and you're driving a Ferrari, your latency is very low. You're flying. Throughput, on the other hand, is the number of cars that pass a specific point every hour. It's the volume. Now, here is the first principle of performance that every senior engineer knows. Throughput and latency are friends until the system gets crowded. Then they become bitter enemies. When a highway is at 10% capacity, adding more cars doesn't slow anyone down. Throughput goes up and latency stays low. This is the happy zone. But as you reach 70%, 80%, or 90% capacity, something happens. It's called the knee of the curve. Because cars are following each other closely, a single person hitting their brakes for half a second, a minor hiccup, causes a ripple effect. Suddenly, the P99 latency for the cars behind them doesn't just go up by half a second, it goes up by 10 minutes. In software, we call this queuing delay. If your CPU is at 95% utilization, it doesn't have the slack to handle a sudden burst of requests. Every new request has to sit in a queue, waiting for its turn. And as we saw in the last video with Little's Law, the wait time in that queue grows exponentially as you approach 100% utilization. This is why in a FANG environment, we almost never run our systems at 100% capacity. We usually throttle or auto-scale at 60% or 70%. We are literally buying low latency by leaving 30% of our hardware idle. It feels wasteful to a junior, but to a senior, that 30% is the insurance policy that keeps the P99 from skyrocketing during a traffic spike. You have to decide, are you building a Ferrari, low latency, or a bus, high throughput? Because trying to build a high throughput Ferrari is how you end up with a system that crashes the moment it gets popular.
Whenever a system is slow, the immediate response from management is usually, can we just add more cores? Can we just parallelize it? And it sounds logical. If one person can dig a hole in 10 hours, 10 people should be able to dig it in 1 hour, right? Well, no. This is where we encounter Amdahl's law, and it's one of those beautiful, cold, mathematical truths that humbles every engineer. Amdahl's law says that the speedup of a task is limited by its serial fraction. Think about it. Even if you have 1,000 workers to build a house, you can't start the roof until the walls are up. You can't start the walls until the foundation is poured. The foundation is serial. It doesn't matter how many workers you have, the foundation takes as long as the foundation takes. The formula is simple but brutal. Max speedup equals 1 divided by s plus 1 minus s divided by n, where s is the portion of the task that must be done serially and n is the number of processors. Let's say you have a piece of code where 95% can be parallelized, but 5% is serial. Maybe it's a single database lock or a global counter. Even if you give that code infinite processors, the maximum speedup you can ever achieve is 20x. You could throw $1 million supercomputer at it, and it wouldn't go 21x faster. You have hit the physical wall of the serial fraction. This is why staff-level optimization isn't about making the fast parts faster. It's about finding the serial bottleneck and shrinking it. When a senior engineer looks at a system design, they aren't looking at the distributed part first. They are looking for the choke point. Is there a single leader node? Is there a single database shard everyone hits? Is there a global lock in the code? If you find a 5% serial bottleneck in a global system, you have found the ceiling of your company's growth, and no amount of cloud scaling will save you from that math. The last thing I want to talk about in this section is the senior engineer's game of whack-a-mole. In a complex system, you are always limited by something. There's no such thing as a perfectly optimized system. There's only the current bottleneck. Imagine you have a slow API. You profile the code and find a slow algorithm. You optimize it. Now the CPU is fast. But suddenly, the API is still slow. Why? Because now that the CPU is fast, you're hitting the database harder, and you've reached the limit of disk I/O. You add a cache to solve the disk I/O. Now the disk is fast, but the API is slow again. Why? Because the cache is so fast that you're now saturating the network bandwidth of your network card. You upgrade to a 10 Gbps network card. Now the network is fast, but the API is slow. Why? Because you've reached the limit of lock contention in your kernel because so many threads are trying to use that fast network card at once. This is the succession of bottlenecks. As a senior engineer, you have to realize that when you fix a performance problem, you aren't making the problem disappear, you're just moving it somewhere else. The goal of system design isn't to have no bottlenecks, it's to move the bottleneck to the place where it is cheapest and easiest to manage. You'd rather be limited by network bandwidth, which you can buy, than by database lock contention, which requires a massive architectural rewrite. Before you start optimizing, ask yourself, where am I moving the bottleneck to? If you don't know the answer, you're just spinning your wheels. You're just changing the color of the wall you're about to run into. So, we've covered the math. We've looked at the distributions, the queues, and the laws of parallelization. But if you're a senior engineer sitting in front of a dashboard at 3 a.m., how do you actually use this? You need a framework for measurement. At Google, we call these the 4 golden signals. If you monitor these 4 things, you have a high-resolution window into the physics of your system. The first is latency, but as we've established, we don't just look at the average. We track the P50, P95, and P99 separately. If your P50 is stable but your P99 is rising, you have a tail problem, probably a resource contention or a stop-the-world garbage collection event. The second is traffic. This is your lambda from Little's Law, how many requests are hitting the pipe. The third is errors, and here's a staff-level tip. Always measure your error rate relative to your traffic. If your errors stay the same but your traffic drops, your error percentage is actually skyrocketing. That's a sign that your system is failing so badly that users can't even reach it to trigger an error. But the fourth signal, the most important one for first principles thinking, is saturation. Saturation is the measure of how full your most constrained resource is. Remember our highway analogy? Saturation is the car density. Most engineers look at CPU or RAM, but saturation can be anything. It can be the number of available threads in a thread pool. It can be the number of open file descriptors. It can be the depth of a message queue. The thing about saturation is that it's a leading indicator. If your CPU saturation goes from 40% to 80%, your latency might stay perfectly flat. Everything looks fine. But because of the knee of the curve, you are now inches away from a latency explosion. Monitoring saturation is like checking the fuel gauge on a plane. You don't wait for the engines to stop, latency, to realize you're out of gas. You look at the gauge. As a senior, you should be able to point to a graph and say, we are at 85% saturation on our database connection pool. Based on our current growth, we will hit 100% in 2 weeks. If we hit 100%, our P99 latency will increase by 500%. That is how you prevent outages before they happen.
Let's put it all together with a real-world staff-level trick. This is something Google uses in its search infrastructure to solve the tail latency amplification problem we talked about earlier. It's called hedged requests. Imagine you're Google. A single search query hits 1,000 different machines to find the best results. As we saw, if each machine has a 1% chance of being slow, P99, the user is guaranteed to have a slow experience. You can't optimize away the 1%. Sometimes a machine just decides to run a background task. Sometimes a network switch blips. So what do? You use the math. The strategy is this. You send the request to the first machine. You wait for a very specific amount of time, let's say the P95 latency, maybe 10 ms. If the machine hasn't responded by then, you don't keep waiting. You send a second, identical request to a different machine, a replica. You take whichever result comes back first and cancel the other. Think about the math of this. For the user to experience a slow response now, both machines have to be in their P99 slow zone at the exact same time. The probability of that is 0.01 times 0.01. That is 0.00001. By adding a tiny bit of extra throughput, sending an extra 5% of requests, you have reduced your tail latency by 100x. This is what I mean by statistical engineering. You aren't fixing the hardware. You aren't even fixing the code. You are using the laws of probability to build a reliable system on top of unreliable components. When people ask, how does FAANGL handle millions of users, it's not because our engineers are 100x faster at writing code. It's because we understand these patterns. We know how to trade a little bit of bandwidth to buy a massive amount of latency. We know how to use the tail to our advantage. All right, we've covered a lot of ground today. We moved from the lie of the average through the amplification of the tail into Amdahl's law and finally into the hedged request strategy. The takeaway is this: scale isn't just more. Scale is different. When you add zeros to your user count, the math of your system changes. Rare events become common, averages become invisible, and bottlenecks become ceilings. If you want to master system design, you have to fall in love with the histogram. You have to look at a graph and see the physics of the queue behind the lines. Here is your senior challenge for video 2. I want you to go to your current project's monitoring dashboard, find your mean latency, and then find your P99 latency. Calculate the P99 to mean ratio. If your P99 is 10x higher than your mean, you have a variance problem. In the comments, post your ratio and tell me if your traffic doubled tomorrow, which one would explode first, the mean or the P99? And based on what we learned about Little's law and saturation, what is the physical resource that will cause that explosion? Is it CPU, RAM, disk I/O? I want to see your diagnostic thinking. In the next video, we're going to look at reliability. We're going to talk about what happens when the physics of software meets the reality of hardware failure. We're going to learn how to build systems that literally cannot fail, even when the machines they run on do. I'll see you in video 3.